Hi, so today we're going to talk about how the exponential function and sine and cosine relate to each other using some calculus. If you haven't studied calculus before, maybe this is a surprise to you that they relate, but I do recommend if you haven't done, say, a section on series to go back and review that first before going through this video, because we're going to use a certain type of series to show this connection. So we're going to use something called a Maclaurin series. Sometimes it's also called a Taylor series, centered at the value 0. But it's this idea that we can approximate a function using the derivatives of that function. So we can say that some function f of x is going to be the sum of the nth derivative of x at some value. In this case, since it's a Maclaurin series, it's at the value 0. And we divide by n factorial and multiply by n x to the n. So for a series like this, we for a series like this, we're going to not go through the proof of why these particular series that I'm about to use are the way they are, but we can show, if you're familiar with the Maclaurin series, that the exponential function e to the x is the sum from n equals 0 all the way up to infinity of xn over n factorial. So that means we are looking at a sequence of polynomials where we have them added up as 1 plus x squared over 2 factorial plus x cubed over 3 factorial. I'm going to just write out a few more terms because I really want to show how these series relate and how it's not just the first few terms. Usually when we're looking for patterns in a series, we want to make sure that we've looked at enough terms to be pretty confident that this does seem to be a pattern that continues and is not just something that satisfies one or two terms. So if I write out the first 7 terms of the exponential function, this is what I end up getting. If I do the same for, say, cosine of x, I end up getting something that is going to look a little bit more complicated in the beginning, but when we write out the terms, we're going to see that it actually isn't too complicated at all. So we get something that is alternating signs, so -1 to the n, x to the 2n, all over 2n factorial. If I write out the first few terms of this, I get 1, I get minus x squared over 2, I get plus x to the 4th over 4 factorial, so it's 2 factorial, minus x to the 6th over 6 factorial. And I think we can start seeing the pattern where we have these even powers, we have the even factorials, and we have something where the sign is changing every other term. If I do sine of x, well, this is going to be a little familiar, but again, gonna look complicated at first. We're gonna have something changing signs, but now instead of 2n, we're gonna have 2n plus 1. And we have 2n plus 1 factorial in the bottom. Sometimes you'll see 2n minus 1, depending on how you're defining the start of your series. But basically, whenever you see 2n plus 1 or 2n minus 1, what we're left with are odd values. So we have x, we have minus x cubed over 3 factorial plus x to the 5th over 5 factorial. And if I wanted to go one more just to continue the pattern, I have x to the 7th over 7 factorial. So using these different Maclaurin series, for these three functions, we're going to now show how they relate. If I look at cosine, I see that, like I said, I have these even terms here, which I'm going to highlight. If I go back to my exponential, I see that those terms show up there every other term. But one of the things that is changing is the sign in front of these terms is not going to be the same. If I now look at my sine function, I have my odd terms. And if I look back at the exponential, I have those odd terms again. But again, we have this issue where in the exponential series, we have only positive terms, but with sine and cosine, we have terms that go from positive to negative. So how can they seem to be some way to relate these, but it might not be clear how we're going to relate them. What I'm going to do is I'm going to say we're going to use complex numbers. So if you haven't used complex numbers in a long time, don't worry, we're going to keep it very simple. We're going to say that I, so the first power, is just I, right? And the definition, remember, of I is that it is the square root. So if I square it, I get -1. So it is the square root of -1. But in order to be complete, I'm going to say I to the 0th power is 1 because any finite number, including imaginary numbers, to the 0th power ends up being 1. If I have now I cubed, well, this is the same thing as I squared times I. So this is just going to be -1 times I, or just -I. So let's just do 1 or 2 more just to feel confident in the pattern that we're seeing here. If I do I to the 4th, well, that's I squared times I squared. So I get -1 times -1, or +1. And let's do one more. So if I have I to the 5th, we can say, well, that's just I to the 4th times I. So this is just going to be I. So what we see here is this cyclic sort of pattern. I go from 1 to I to -I, to -1 to -I, and then back to 1 to I. So I could expect then that I to the 6th is going to be -1, and I to the 7th is going to be -I. And we're going to use that fact now and say what happens if we find e to the ix as a Maclaurin series. Okay, so what I'm going to do is I'm going to take our definition of a Maclaurin series, which we said was, let's remind ourselves, n equals 0 to infinity of x to the n all over n factorial. But now I'm going to say I'm going to plug in ix, and that means in my series, I am also going to plug in ix. So let's see what happens when we start writing out these terms. I'm going to move this here so I can just start writing the terms out side by side. So again, we're going through, we have 1 as our first term. We end up having ix over 1 factorial. We have I squared x squared over 2 factorial. We have I to the 3rd x cubed over 3 factorial plus I to the 4th x to the 4th over 4 factorial plus I to the 5th x to the 5th over 5 factorial. And I'm going to stop at I to the sixth, x to the sixth over 6 factorial, but we know this continues. So now let's simplify by actually plugging in these values for I squared, I cubed, etc. So I end up getting 1 plus ix minus, because of the I squared, x squared over 2 factorial, then minus I x cubed over 3 factorial plus x to the 4th over 4 factorial plus I x to the 5th over 5 factorial, and then minus x to the 6th over 6 factorial, and this would keep going. So this now should feel really familiar compared to what we wrote a few moments ago. But let's start reorganizing these. What I'm going to do is I'm going to say that some of these values are going to be pink. So this one, this whole one, this one here, and this one here. And some of these values are going to be green. Now, why I'm doing this, I'm splitting up those even powers and those odd powers. So I have for my even powers, 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial. And that now should be something that you recognize as the Maclaurin series of our cosine function. If I now include my green terms, well, it looks pretty similar to the sine function that we wrote earlier, but we have this one difference in this. The big difference here is that we have, and I'll do this in another color, the big difference here is that we have this I out in front, but it's out in front of every single term. Since it's out in front in every single term, well, I'm going to just pull that out. So I have 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, etc. But then I also have plus I x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, etc. And we have already said above that this here is the sum from n equals 0 to infinity of -1 to the n x to the 2n over 2n factorial. And then this here is negative, the sum from 0 to infinity, -1 to the n, x to the 2n plus 1, all over 2n plus 1 factorial. And we've said that this is our cosine of x, and this is our sine of x. So we have just showed that e to the ix is cosine of x plus I sine of x. And this is called Euler's formula. Euler was has a lot of things named after him, but this one is very useful. It comes up a lot in I use it a lot in physics and things like that. And I think there is a what is it? A specific example that people like to show that, well, what if x equals pi? Well, if I use this relationship between exponential, sine, and cosine, what I end up getting is e to the I pi equals cosine pi plus I sine pi. Or e to the I pi equals equals -1 plus 0, and that we have all of these very common important values of mathematics showing up in the same formula, that being the pi, the 1 or -1, and 0, as well as I. So this is just a very important result using Maclaurin series. We didn't really go through why we can plug in a complex number into an exponential. That's for another time. But this, again, is something that I use all the time in calculations, and it's really important to know why we get that relationship.